Hi, Stu Schwartz from MasterMathMentor.com. This is video AB22. The topic is optimization, and it covers the AB manual pages 135 through 138. Here is a problem that I faced many times when I lived just outside of Philadelphia. Frequently, I would find myself at the massive King of Prussia Mall and needed to get home. I needed to find the best way to get home. This is a map of the area, and you can look at it and decide which way you would go if you wanted to get from the King of Prussia Mall back home. There were generally two ways to go. One was the direct route up Route 202 through the towns of Bridgeport and Norristown, and eventually ending up north at home, which was about a distance of 12 miles. I could also get home using toll roads. I can travel along Route 276, which is the Pennsylvania Turnpike, to the town of Plymouth Meeting, and then get on Route 476, which is an extension of the Turnpike. The distance is about 20 miles. This is an optimization problem. When we optimize, we are interested in finding the best solution. Of course, we have to define what best means. If by best we want the shortest distance, then obviously we take Route 202. If best means the shortest time, then most likely we would take the interstate, because we can travel fast, assuming there's no traffic. If best means the cheapest, we would take Route 202, because the Pennsylvania Turnpike is Route 476, and that costs money. If best means least risky, we would also take 202, because once we're on an interstate and there's a traffic jam, we're stuck, whereas with 202, we could go onto side streets. This video will deal with optimization problems and how to make the decision which is the best route to take. On page 136, there is a general method for solving optimization problems. You can read it through, and when we analyze problems, we will go into those steps in more depth. But for now, we will summarize that method with this flowchart. Our first job is to assign variables for all quantities. Secondly, we will make a chart or a table that shows the relationship between the variables and will give us a feel for the problem. We will then write a primary equation for the expression to be optimized. If this primary equation has more than one variable, we're going to need a secondary equation. We will use the second equation so that the primary equation has one variable. We will then take its derivative and set it equal to 0. Our answer will be either a maximum or a minimum. We can use our tests to determine which. If there are endpoints, we must test them as well. And finally, we will answer the question that is asked. Probably the most important step is step 3, where you're asked to write a primary equation for the expression to be maximized or minimized. In order to do that, you have to look at the problem and search for words that indicate that you're to take a maximum or minimum. So, for instance, you might see the words largest area. And if so, your primary equation would be A equals some expression. If you needed to find the smallest amount of wood, then your expression would be W equals. If you wanted the least amount of medication, then your primary equation would be in the form of M equals. If you want to maximize the profit, get the largest possible profit, then your statement is P equals. If you want to do something with the least cost, then your expression is C equals. If you want to travel in the shortest amount of time, then your expression is T equals. I advise you to go through the classwork problems and the homework problems and underline those key expressions that will tell you what your primary equation will look like. Problem number 1 reads, two numbers sum to 40. Find the numbers that maximize their product. Complete the chart. The first thing we do is assign variables. I decided to call the smaller number x and the larger number y, even though we don't necessarily know that one of the numbers will be smaller than the other. The product will be called p. I then make a chart with different combinations of numbers that add to 40. For instance, 1 and 39, 2 and 38, etc. And then I find the product. And I notice that for different values, the product is large and sometimes it is small. The next step is probably the most important. You needed to find the numbers that maximize the product. Note that I underlined them because those are the key words, which means that we need a statement about the product. So our primary equation will be P equals XY. This primary equation has two variables on the right side. We must reduce it to 1, which means that we need a secondary equation, or sometimes called a constraining equation. This is written as x plus y equals 40 because you were told that the two numbers sum to 40. We solve for either of the variables, usually the one that's easiest. In this case, either is easy to solve for. Y is equal to 40 minus x. We go back to the primary equation, replacing the y with 40 minus x. And we get P equals x times the quantity 40 minus x, or P equals 40x minus x squared. We now take the derivative. 0 equals 40 minus 2x. And we get 2x is equal to 40, and therefore x is 20. And because y is 40 minus x, y is 20 as well. We could use our first or second derivative test to determine whether these numbers represent a maximum or minimum. However, looking at the chart, it's clear that it represents a maximum. The product of 20 and 20 is 400, and it is clearly the maximum because we see values that are smaller than that. There is no minimum because one of the numbers could be negative, making the other large number a large positive. For instance, when x is negative 10 and y is 50, then the product is negative 500. So here's a problem that has a maximum but no minimum. The answers are x equals 20 and y is equal to 20. In number 2, you're asked to find two positive numbers, a and b, that minimizes the sum of twice a and b if the product of the two numbers is 288. Again, we're asked to make a chart. In the chart, we label the numbers as a, b, and the sum is s. And I put in several combinations of numbers whose product is 288, and then looked at the sum of twice a and b. So when a is 1 and b is 288, then the sum is 290. That is different if a is 288 and b is 1. That sum is 577. There's obviously an infinite number of combinations of numbers that multiply together to give 288. We want the one that minimizes the sum of twice a and b. I underlined the key words, and our primary equation is s is equal to 2a plus b. There are two variables on the right side, so we need a relationship And our secondary relationship is AB equals 288. We then solve for one of those variables, and it is probably easier to work with B because with A we'd have to double it. So B is equal to 288 over A. Going back to the primary, we get S is equal to 2A plus 288 over A. Taking the derivative, we get 0 equals 2 minus 288 over A squared. And that gives us 2A squared is equal to 288. And A squared is equal to 144. And because A is positive, A equals 12. Therefore, B is 288 over 12, which is 24. You should confirm to yourself that these two numbers, 12 and 24, represent the minimum sum of twice A and B. If we look at twice A plus B, we get 48. And it's clear by our chart that there are combinations that give us larger values. In this case, there is no maximum sum of twice A and B, only a minimum. Number 3 states that a rectangle has a perimeter of 71 feet. What is the maximum area of the rectangle? We call the width X, the length Y, and the area A. Realizing that if the perimeter is 71 feet, then the half of the perimeter is 35.5 feet, and that must be the sum of the width and the length. So again, some combinations are shown. The width is 10, the length is 25.5. The width is 1, the length is 34.5, etc. Again, you are doing this just to get a feel for the problem. Our primary equation is based upon the underlined words maximum area. So A equals xy. There are two variables on the right-hand side, so we need a relationship between x and y. And we use the fact that the perimeter, which is 2x plus 2y equals 71, and therefore y equals 35.5 minus x. Therefore, A equals x times 35.5 minus x, or 35.5x minus x squared. We take the derivative and set equal to 0. So 0 equals 35.5 minus 2x, and that gives x is equal to 17.75, meaning that y is equal to 17.75. So our answer is that our rectangle is a square. It is very important to answer the question. It did not ask for the dimensions of the maximum area rectangle. It actually asked for the maximum area. So you actually have to multiply x and y and get that A is equal to 315.0625 square feet. Also very important to make sure you have the correct units in your answer. Also, this has to be the maximum area because if we look at some of the other areas that we found, they are clearly smaller. Number 4 reads, an open box is to be made from a piece of metal 16 by 30 inches by cutting out squares of equal sides from the corners and bending up the sides. What size square should be cut out to create a box of greatest volume? And what is that maximum volume? Complete the chart. Shown is the piece of metal 16 by 30. We now cut out little squares from each of the corners. Being metal, we then bend up the protruding sides to get an open box. Depending on the size of the square, we can get a box that is long and wide, but not high. A box that is shorter and less wide, but higher. A box that is very short and narrow, but also quite high. And pretty much anything in between. The question is, which gives the maximum volume, and what size square should we cut out to create it. Let's go through the steps in actually solving this problem. First is to create a sketch. Many times they are provided for you. In this case, it was not. So we see our piece of metal, 30 by 16, and the little squares that are going to be cut out from each corner. We will say that they have dimensions x by x. Making a chart or table is not really necessary to solving the problem. However, the primary equation must be in terms of variables, in this case x, and working with numbers is easier at first for students and gives them a feel to how to actually write that primary equation. We see that when x is 1, that makes the length 28 and the width 14, giving a volume of 392. And x of 2 makes the length 26 and the width of 12, and the volume is increased. We see through different values of x that the volume increases, but then it decreases. And that suggests that there must be an absolute maximum. So, when x is the side of your square, the length is 30 minus 2x, the width is 16 minus 2x, and therefore the volume will be x times 30 minus 2x times 16 minus 2x. So we have our primary equation that V is equal to x, quantity 30 minus 2x, times quantity 16 minus 2x. Expanding that, we end up with V is equal to 4x to the third minus 92x squared plus 480x. Taking the derivative, we get 0 equals 12x squared minus 184x plus 480. We can factor out a 4 and get 3x squared minus 46x plus 120, and that factors into 4, quantity 3x minus 10, quantity x minus 12, meaning that x is equal to 10/3 inches and x is equal to 12 inches. It is impossible to have a 12-inch square cut out because the width is 16 inches. So we throw that out, and that tells us that x must be 10/3 inches, saying that the max value, plugging in the value of x to our primary, is 725.926 cubic inches. There is no minimum value. As the sides of x get smaller and smaller and smaller, the volume will get very, very close to 0. On the introductory problem, we had a choice of traveling directly from the King of Prussia Mall to home via Route 202, a distance of about 12 miles, through several small towns and numerous traffic lights. Or we could travel along the toll roads, Route 276 and 476, which is the Pennsylvania Turnpike, a distance of about 17 miles. Let's suppose that we would like the optimal solution in terms of time. We know from bitter experience that no matter what time of day, we could expect to hit a lot of traffic lights along Route 202, and the best we can average is about 35 miles per hour. Therefore, the time is equal to our distance over our rate, which is 12 over 35 over 60, and we end up with getting a time of approximately 21 minutes to get from the King of Prussia Mall back home. For the amount of time to be the same taking the toll roads, our speed would have to be 17 divided by 21 over 60, which is about 49 miles per hour. If we travel 49 miles per hour on the toll roads, we could expect that it would take about 21 minutes. So if I know that I can average better than 49 miles per hour on the toll roads, then in terms of time, that's the optimal way to travel. I could check out some travel apps to see if there are any issues on the Pennsylvania Turnpike. However, things can change in a flash, and I might find that if there was an accident directly in front of me, I may have made a very bad decision. There is no calculus here. There are only two decisions, to take Route 202 or the Turnpike. But if there were other options, like getting off the Turnpike early and traveling a diagonal road to home, I might be able to cut my time further. That's a calculus problem. Let's see an example of that very thing. In number 5, we are told that I am 1 mile off the coast and wish to get to a town 3 miles down a rocky coast, as shown in the figure to the right. I need to swim to shore and then walk along the shoreline. I want to know at what point X should I swim to along the shoreline so that the time it takes to get to the town is a minimum. We know that I can swim at 2 miles per hour and walk at 4 miles per hour. We have a chart to complete as well. The chart is time consuming to fill out, but once you do, you will find that the solution almost writes itself. Let's let X be the distance from the perpendicular to which you swim. If X is 0, then the swimming distance is 1, making the walking distance 3. Therefore, the swim time at 2 miles an hour is 1 divided by 2, or 1/2. And the walking time is 3 divided by 4, which is 0.75. So it totals 1.25 hours if we swim directly to land. This is the safest route as you are in the water the least amount of time. Now let's suppose that we swim directly to town. That makes X is equal to 3. So the swimming distance is the hypotenuse of the right triangle with sides 1 and 3, giving the square root of 10. And there is no walking distance. So the swimming time is simply the square root of 10 divided by 2, and the walking time is 0. So the total time is 1.581 hours. This might be the shortest distance that you travel, but since it's all spent in the water and you don't swim particularly fast, it's going to take you more time. So rather than look at these extreme cases, let's let X equal some value between 0 and 3. Suppose X is 1. That means our swimming distance is the square root of 1 squared plus 1 squared, which is the square root of 2. And our walking distance is 3 minus 1, or 2 miles. So our swim time is the square root of 2 over 2, and our walk time is 2 over 4. Add those up, and we get 1.21 hours. So we have shaved off a little bit of time by going 1 mile in from the perpendicular. Can we do better? That's where calculus comes in. So if we swim to point X, our swimming distance is the square root of X squared plus 1 squared, and our walking distance is 3 minus X. Therefore, our swim time is the square root of X squared plus 1 over 2, and our walking time is 3 minus X over 4. Therefore, the total time is the square root of X squared plus 1 over 2 plus 3 minus X over 4. So our total time can be written as the square root of X squared plus 1 over 2 plus quantity 3 minus X over 4. Taking the derivative and setting it equal to 0, we get 1/2 times x squared plus 1 to the negative 1/2 times 2x all over 2, which gives x over 2 square root of x squared plus 1 minus 1/4. We then take the 1/4 over to the other side and cross multiply, and we get 2x is equal to the square root of x squared plus 1, or 4x squared equals x squared plus 1. 3x squared equals 1, and therefore x is equal to the square root of 1/3, which is 0.577 miles. So our total time is 1.183 hours, which is just slightly less than the 1.21 hours we calculated when x was 1. There is a maximum time, and that is 1.581 hours, when our walking distance is 0 and we are swimming directly to town. We can verify our results graphically by graphing the expression y equals the square root of x squared plus 1 over 2 plus quantity 3 minus x over 4. We see the minimum occurs at 0.577, 1.183. Or you could graph the derivative of that function and find out where it is equal to 0. It will occur at 0.577. Problem 6 reads, show that the dimensions of the largest area rectangle that can be inscribed into a circle of radius 4 is a square. Use your proof to show that the largest area rectangle that can be inscribed into a circle of radius r is also a square. Inscribing problems go hand in hand with optimization readily. This is one of the easier types of inscribing problems. There are infinitely many rectangles that can be inscribed into a circle. There are tall, narrow ones. There are shorter and wider ones. We want to show that the largest possible area rectangle that will inscribe into a circle of radius 4 is a square. And what's more, the radius of the circle is irrelevant. The rectangle will always be a square no matter the size of the radius. We forego the chart here. Developing dimensions for possible rectangles that could inscribe into the circle is just too time-consuming. We write the sides of our rectangle as x and y. We do not use x and x because we do not know it's a square. That's what we're trying to prove. And since the radius is 4, the diameter is 8. So our primary equation is a is equal to xy. Since there are two variables on the right-hand side, we must have a relationship between x and y. And because of it being a right triangle, we know that x squared plus y squared equals 64, and y is equal to the square root of 64 minus x squared. So the area is equal to x times the quantity 64 minus x squared to the 1/2 power. By the product rule, we take the derivative, getting x times 1/2, 64 minus x squared to the negative 1/2 times negative 2x, plus 64 minus x squared to the 1/2 power. From there, we can write x squared over the square root of 64 minus x squared is equal to the square root of 64 minus x squared. Cross multiplying, we get x squared equals 64 minus x squared, and that gives us x is equal to 4 square root of 2. And plugging in for y, we get y is equal to 4 square root of 2. So we have proved that the largest area rectangle that can fit into a circle of radius 4 is a square with dimensions 4 root 2 by 4 root 2. To show that the dimensions of the largest area rectangle that can be inscribed into a circle of radius r is a square, we just change our proof slightly, realizing that our radius is r, so our diameter is 2r, and our secondary equation becomes x squared plus y squared equals 4r squared, or y is equal to the square root of 4r squared minus x squared. So we now replace our y with 4r squared minus x squared to the 1/2 power. Everything remains the same, and we end up getting x squared equals 4r squared minus x squared, and therefore x is equal to r root 2 and y is equal to r root 2. Number 7 reads, a 6-ounce aluminum can of Friskies cat food contains a volume of 14.5 cubic inches. How should it be constructed so that the aluminum used to make the can is a minimum? There are an infinite number of ways that we can construct a cylindrical can containing 14.5 cubic inches. Watch as we generate a number of them. Since we want to minimize the amount of aluminum used, we define A to be the surface area of the can, R to represent the can's radius, and H to represent the can's height. The area will be the side, whose area is 2 pi RH, and the top and the bottom, which are circles, plus 2 pi r squared. There are two variables on the right-hand side, so we need a secondary equation. We utilize the fact that the volume must be 14.5 cubic inches, or pi r squared h equals 14.5. We need to solve for a variable, and it is clear that h is easier to solve for than r. So h is equal to 14.5 over pi r squared. So, substituting, a equals 2 pi r times 14.5 over pi r squared plus 2 pi r squared. That gives 29 over r plus 2 pi r squared. And taking the derivative, setting equal to 0, we get negative 29 over r squared plus 4 pi r. And therefore, bringing the 4 pi r to the right side, we get r cubed is equal to 29 over 4 pi, and therefore r is the cube root of that expression, and that turns out to be 1.321 inches. Therefore, the height is 14.5 divided by pi times 1.321 squared, and we get the height to be 2.643 inches. So we find that the most efficient can in terms of aluminum used will be one whose diameter and height are the same size. Here is graphic confirmation of our answer of r equals 1.321 inches. Notice that there is no maximum surface area. If r is very, very close to 0, then h will be very, very large, and the surface area will be huge. The same is true if r is very, very large, then h will be very, very small, but the surface area will still be enormous. This is the actual size of a can of Friskies cat food. This is what the can would look like if it used the optimal amount of material and the height and diameter were the same. Why isn't it? It may be that the cost of the top and bottom of the can, which is made of very thin aluminum, may be different than the can itself. In that case, there is now an economic aspect to the problem. We will examine economic optimization in the next video. Stay tuned.